Okay, so you can build up any matrix you like. When you do, the row space of that matrix is still going to be the same as the row space of this matrix, right? Because you got that matrix by doing valid row operations. Every row operation has an inverse, which is also a valid row operation. So if you build up a matrix from this using row operations, you can bring it back to this just by using the inverse row operations. Now, so the row space of this matrix just consists of the one vector, 0, 4, 1. That's it. Okay? The null space of this matrix. Okay? Well, you only get one equation out of this, which is 0x1 plus 4x2 plus x3 equals 0. You get a free variable out of this. Let's let x2 be the free variable, call it t. Okay, then x3 will be negative 4t, because you got 4t plus x3 equals 0. It's clear that this is your solution. And then that addresses x2 and x3. What about x1? Well, the equation doesn't even mention x1. Now some people will think that means x1 must be 0 because you got a 0 here. Okay, but that's not the case. X1 can be anything, can take any value. So we're going to let x1 be s. Let s be the value of x1. And x1 is a free variable, right? You've got one equation and three unknowns. Just because one of the unknowns doesn't appear in the equation, it still applies to the system with three unknowns. You've got two free variables, okay? We chose x3 as a free variable, and x1 has to be a free variable because it doesn't appear. Our null space basis then be what? Okay, well, along with x1 equal s, okay, we can let x2 and x3 be anything we like, but we're just going to make them 0, okay? S and any two numbers will give you a basis vector, but we might as well keep it as simple as possible by saying it's s, 0, 0. Perfectly valid situation. x1 equal to s, x2 equal to 0, x3 equal to 0. Well, that certainly satisfies this equation, right? So that's a valid vector in the null space. And then you have the vector that you would get out of this, okay? Now, again, x1 can be anything, okay? But now that we've said that x1 is s, we could have put an s here, okay? But we don't have to. We can use just 0, and then t, that's our x2, and negative 4t, okay? So there's a basis for the null space. Well, actually, the basis would be this, as I say here, for any s and t you wish to use, along with the idea of keeping it simple and maintaining the idea of keeping it simple. We're going to let s and t both be 1. So this vector becomes 1, 0, 0. This vector becomes 0, 1, negative 4. Okay, so there are the basis of our row space and our null space. So the picture is kind of like this, but in this case our null space is spanned by two vectors. It's a plane. We can see what the plane is. We come out from the origin, we come out 1 unit in the x direction. That's this vector. Then 0, 1, negative 4. No motion in this direction, 1 unit in this direction, and 4 units down in this direction. So our basis vectors, not sure what to do with that third arrow, okay? Our basis vectors might have these directions. Now this one would be 4 times as long as this one, but that's a perfectly good basis, okay? So there's our null space. Any vector through the origin, or any vector in this space, okay? We model it with a plane through the origin, so any vector from the origin to any point on this plane gives us a vector in the null space. And the row space is just span of this vector. No units in this direction, 4 units in this direction, 1 unit in this direction. So that vector would be kind of like this. So here's your null space, here's your row space, and here's your null space, okay? And as it turns out, the two are orthogonal, they're perpendicular. And you can verify that by doing the dot product, okay? Dot product of this with this is clearly 0. The dot product of this with this is easily seen to be 0. Okay, now we have that. Let's talk about the column space, because now you've been able to construct this into a matrix that's less obviously one that reduces down to the rows of zeros, okay? Get rid of the rows of zeros. So we'll address that next.